This
She has
conference will
enough
now be
research
recorded.
experience in industry. Over and above, she holds professional experience of about 25 years. She was the winner of Young Scientist Award in the year 2008. She is a research supervisor under APJ Abdul Kalam Technological University. Currently, she is supervising 5 research scholars in the field of optics and holography. She is an invited speaker to Tianjin University, China, and Jamia Millia Islamia University, New Delhi. She has research funding from different funding agents like ASCSTE, Government of Kerala, and CERD by APJ Abdul Kalam Technological University into her credit. She is the capital person in setting up research lab in the institution. She has many research publications in nationally and internationally reputed science citation index journals. She got the honor as a reviewer in a few science citation index journals, especially in optical engineering and Journal of Electronic Imaging published by SPIE. She is an external doctoral committee member in APJ Abdul Kalam Technological University, Kerala University, Anna University, NI University, etc. Now, on behalf of Government Model Engineering College, Kochi, let me invite Dr. Sheeja MK to deliver her lecture on holographic data storage technology. Over to you, ma'am.
Can you hear?
Yes, ma'am.
Okay, I will share my presentation. Presentation is okay?
Yes, ma'am.
Okay. So good afternoon one and all. I am Dr. Sheeja MK and my presentation is on holographic data storage technology. First of all, let me
Sorry
thank
to interrupt you,
Dr.
ma'am.
Laila. Okay,
Can you make it as full screen?
1 second. One minute. Is it okay? Is it okay?
Ma'am, can you press Control and L?
1 minute.
Yeah.
Is it okay?
No, we can't see the presentation. Can you please share the screen?
Okay, once again. Now is it okay?
No, ma'am. We can't see the presentation.
Okay, once more I will share. Okay. Now it's okay?
Okay, ma'am.
Okay, thank you. So first of all, let me thank Dr. Laila, the coordinator of the AICT sponsored faculty development program, and Professor Sadish for inviting me to deliver a talk in this particular uh, training program. So let me give an overview about my presentation. So introduction, then principles of holography, transmission and reflection holograms, recording and reconstruction of holograms, applications of holography, holographic data storage, impacts and interesting facts, and conclusion. So what is mean by holography? It's a method of recording whole information. Holo is a Greek word. Holo means whole view, W-H-O-L-E, whole view, and gram means writing or drawing. So holography means it's a method of recording the 3D information or the whole view of the information. So these are some of the familiar holograms, the Dow, as you can see in your credit card, and this is the hologram of the inventor or the founder, Dennis Gabor. So history of holography comes in the year 1947. It starts in the year 1947. It was invented by a Hungarian physicist, Dennis Gabor. In the year 1979, he lived in the year 1900 to 1979, and who got a Nobel Prize in 1971 for his invention, the principles of holography. You may be wondering how it looks like a hologram. Actually, it is a 3D view. This figure is a character in the Star Wars movie, that is Yotha. This image is a hologram. It's a computer generated hologram. It has a full view. It is not 3D. So that is a peculiar to hologram. That means you will get a 3D perspective of the object. What is the difference between holography and photography? We are familiar with photography. It is recording only the intensity of the object. But in holography, both intensity and phase are recorded. So, due to the recording of intensity and phase, we are getting a full view or 3D view of the object. So holography is the science of producing holograms. It's an advanced form of photography that allows an image to be recorded in 3 dimensions. If the hologram is broken into parts, that means if the glass piece containing the hologram is broken, even a small piece is capable of reconstructing the entire object. But in photography, the destruction of even very small portion of negative or photography results in an irreparable loss of information, and also it has high information capacity as compared to photography. Comparing with photography, black and white photograph, it records only intensity. If it is a color photograph, it records both intensity and wavelength. And it is a hologram means it records both intensity and phase of the object. So since it is recording the intensity as well as phase, we will get a 3D perspective of the object. So for producing a hologram, we want a highly coherent source, which is a laser beam. So create a hologram, a laser beam is split into 2 beams. One is the reference beam that stays undisturbed. That means from the laser, it travels undisturbed to the recording medium. And another one is the object beam. It strikes to the object, and after diffraction, it bounces back to the same holographic plate. So the 2 beams are allowed to interfere on the same area on the holographic plate, and we will get a hologram. So the starting point is a laser, a highly coherent beam. It is split using beam splitter into 2. One is the reference beam and another one is the object beam. And the reference beam, it doesn't carry any information. The object beam carries the information which we want to record. So the object beam means is a light diffracted from the object. The 2 beams are allowed to interfere on the holographic material and a hologram is recorded. So the lasers normally used in holography are continuous wave lasers, helium neon laser 632.8 nanometer. It is a red region. Helium cadmium laser 442 nanometer. Then argon ion laser 540 nanometer green and 476 nanometer blue. And also pulse laser also used. Ruby laser 694.3 nanometer, which is in the deep red. In this pulse laser is used for taking the holograms of moving objects. And how it works. The basic principle behind holography and principle behind holographic data storage, both are same. Only thing, one or two components will vary in holographic data storage. So the basic principle of holography is it is the works under the principle of interference and diffraction of light. Interference, these two are the basic phenomena occurring in holography, interference and diffraction. Interference means the phenomena where two coherent waves overlap to produce a resultant wave of either greater, lower, or the same amplitude. If the two intensities are of the same phase, it will add up. As out of phase, it will be neutralized, or the lower value, you will get the negative value. So the interference is the phenomena where two coherent waves are allowed to overlap. Both intensity and phase will get overlapped. And the other phenomena is a diffraction, the phenomena of bending of waves around the corners of the obstacle or aperture. And the working, we can divide it into two parts. First part is recording of the hologram, and second part is the reconstruction. So this is schematic diagram shows how recording, hologram recording and reconstruction takes place. A very simple diagram. So as you can see, the laser beam is split into two. One is the object beam and other one is the reference beam. The middle portion is the hologram, that is the material, and the two beams are allowed to interfere on a small area in the holographic plate. So that interference pattern we are calling as hologram. So if you want to reconstruct or retrieve the original object, you have to illuminate the, you have to cut the object beam and illuminate the hologram with the reference beam only. That is the second figure. They illuminate. This is the reference beam. Illuminate this portion. This is the hologram portion with the reference beam only. Then you will get a real image in the other side of the area. You will get both a virtual image and a real image. So normally this is the direction of the real image. Then the opposite direction. This is the direction of the virtual image. The diagonally opposite. This is the direction of the virtual image. The mathematical relations. So since the laser light is divided into object beam and reference beam, we can write it as E is equal to R plus O. R is the reference wave and O is the object wave. So R equal to R e raised to I phi comma omega t, and O equal to O e raised to I into I into phi comma omega t. So the recorded intensity I is equal to modulus of R plus O the whole square. So the modulus value will be equal to, when you expand, r e raised to j omega t and O e raised to I phi minus omega t. The value will be equal to r square plus O square plus 2 ro into cos omega minus, sorry, phi minus omega t. So first diagram is for recording. So you can see the reference beam, it is coming, and this is the object, and this is the diffracted light from the object. So O is the object beam. So this is the object and this is the diffracted light from the object. So object beam and the plane reference beam R, you can see R reference beam, they are allowed to interfere, and the XY coordinate axes are shown. So this overlapping area is the hologram. So the intensity recorded can once again written as I is equal to modulus of R plus O the whole square equal to R square plus O square plus 2 RO into cos phi minus psi. That's I is equal to omega t. Again I is equal to, since it is modulus of R plus O the whole square, we can write it as I is equal to R plus O into R plus O the conjugate. So when you expand it, it will be equal to R square plus O square plus R conjugate into O plus R into O conjugate. So the reconstruction process means you have to retrieve the original image back. So you have to cut the object beam. After recording, you can cut the object beam, and in order to reconstruct, you only give the reference beam to the hologram. So this is the portion where hologram resides, and the reference beam is directly given to the, or the hologram is illuminated with the reference beam. So you will get an object beam, which is here, it is placed here, this is a real image, and another one is the virtual image. So reconstruction, the transmitted beam can be written as T, can be represented by T. So R reference, O object beam, I is the total intensity of the hologram, and the reconstructed wave can be represented by capital T. So T, the transmittance value, the reconstructed object nearly equal to R square plus O square plus R conjugate O plus R into O conjugate. And usually R will be in the form of e raised to minus j omega t. The modulus value of e raised to j omega t is 1. So, and also the reference beam is always a plane beam. So it can be equated to unity. So the transmittance nearly equal to R square you can replace with 1. So R modulus value of R e raised to j omega or e raised to j omega t is 1. So transmittance nearly equal to 1 plus O square plus O plus O conjugate. So this term contains, now transmittance contains only the object terms. So you can reconstruct the original signal back or the original object back. There are two types of holograms. One is the transmission and another one is reflection hologram. In transmission hologram, both the waves, you can assume this as the object wave and this as the reference wave, both these are allowed to overlap on the same side of the holographic material. That means both the waves are coming from the same side. Two plane waves, they are coming from the same side and are overlapping in the same side of the holographic material. So it is called a transmission hologram. So transmission holograms are created by two plane waves traveling towards the same side of the recording material. But in reflection hologram, the two plane waves are traveling from opposite sides. So this is one wave and this is so another wave. So they are overlapping in the depth of the material. So this can be called as a volume hologram. So here it's overlapping on one side, transmission hologram, but here it is overlapping in the interference patterns are recorded in the volume of the material. So the characteristics and requirements of the material should be such that it should have high resolution within the volume so that the fringes can be recorded easily. So the two plane waves, when they are traveling in opposite directions of the recording material and interfering, it is called a volume hologram. So coming to white light holography. Normally the holograms are visible using white light. That means the holograms in the credit cards and certificates, holograms embossed on the certificates, holograms embossed on the books. All these are visible in sunlight. That means they are called white light. White light holography is originated by a famous scientist, Russian scientist, Yuri Denisov. So this is a famous scientist who is the father of white light holography, Professor Y.N. Denisov, Yuri Denisov. He invented white light holography. That means even if we are recording it with a red laser or a blue laser, we can illuminate with the white light. The only thing is the if we are recorded it using a red light, the red light will be only be diffracted and we will be able to see the hologram. So all these holograms come under the category embossed holograms, which are in the credit card, books, certificates, etc. for using for the security purposes. All these come under white light holography. They are called as embossed holograms. So this is another interesting one. So white light viewing. So these the scientists who contributed much to this area, white light holography. So again, volume hologram or the reflection hologram, its immersion thickness should be very, very greater than fringe spacing. It can be used to reproduce images in their original color when illuminated by white light. So usually volume holograms or the reflection holograms are come under the category embossed holograms or illuminated by white light. So for a reflection hologram, since it is illuminated by white light, the immersion thickness should be very, very greater than the fringe spacing. It is called a volume hologram. So can be used to reproduce images in their original color while illuminated by white light. We can use multiple exposure of the scene in three primary colors: red, green, blue, etc. So the famous recording materials are silver halide, dichromated gelatin, photoresist, etc. All these three are come under the category wet processing. That means after recording, you have to develop it, then wash it again, fix, rinse, etc. So some chemical processes are involved in processing of the hologram. So silver halide, dichromated gelatin, photoresist, etc. come under wet processing method. Photopolymer and photorefractives, especially lithium niobate crystal, all these come under dry processing. That means they doesn't need the developing and fixing operations. So directly we can record. Holography data storage, we are using these two materials, photopolymer lithium and lithium niobate crystal. That means we will record the data either inside a lithium niobate crystal or in a photopolymer. For data storage, these two are the important materials, photopolymer and lithium niobate crystal. And one more thing, this area is only under research, it is in the developing stage. So the materials available means they are not readily available in the market for experimental purpose, etc. Because the companies who are working in this particular area all are aiming to patent their works, all are aiming to commercialize their products. They are aiming to target the market. So all these are under secret custody. So only experimental purpose materials will be available for laboratory purposes. So photopolymer, we are getting only a less, what we say, it's not up to the quality, it is not good. But even if we can perform experiments in our laboratory using the available photopolymer materials, and also the lithium niobate crystal also of that strategy. Once the holographic data storage devices come into the market, the materials will also come into the market, and we will be readily they will be readily available for recording. So another area is digital holography. Up to this, we have heard that we need a material to overlap the object beam and the reference beam. Without the material, also we can record the hologram. That is called digital holography. In digital holography, this is also a newly advanced area, and some of my students are doing research in this particular area. So in digital holography, we don't need a medium. That means the interference pattern is directly recorded, sorry, or directly collected or grabbed using a CCD camera. So digital holography is a computational imaging technique. In conventional holography, interference takes place on a photographic plane. But in digital holography, we use a charge coupled device CCD to record the interference pattern. That means the beams are allowed to interfere and to fall on the CCD camera. So it is directly grabbed to the computer. And there is a software, H digital software, which is available, and it is developed by VCC. We are working on that. It's digital software which can be used to perform the reconstruction of the digital holograms. This is a schematic diagram. So coherent illumination is there. The object, you can see the object beam is coming, the reference beam is coming. Both are allowed to interfere on the CCD camera. No material is there, no chemical process. So directly grabbed in the CCD camera and stored in the computer. And this is another optical setup for digital data acquisition. You can see this is a laser. Up to CCD camera, conventional holography and digital holography are same. The only difference is in conventional holography, in place of the CCD camera, you have to place a holographic plate or the recording material. If recording material is here, it is a conventional hologram acquisition. If it is replaced with a CCD camera, it is digital hologram acquisition. So in optical setup for digital hologram acquisition, the laser beam is split into two. This is the beam splitter. This is a symbol of the beam splitter. One is the reference beam and another one is the object beam. So this is the reference beam. Since the diameter of the laser is very, very less, it is given to a special filter, and the dia is somewhat increased, and it is allowed to fall on the CCD camera or on the material. If it is conventional method, it is allowed to fall on the material placed here. The other one is called the object beam. The second beam, the object beam, directly goes to the object. So this is the object which creates the object beam. So the spatial filter is again used here to increase the diameter of the laser so that it can illuminate the object fully. Here a fingerprint pattern is shown, and the diffracted light from this pattern is stored in the CCD camera. So here you can see electronic shutter. It is used to control the exposure time. So how much time you are allowing the two beams to interfere on the material or on the CCD camera, because you have to stabilize it. So usually it will be time will be very short. And also depends on the material also. If you are using the dichromated gelatin or silver halide, the exposure time will be different. So the recording time or the exposure time can be controlled by this shutter. So beam splitter used to split the two beams. Then mirrors, they are used to, two mirrors are here, one mirror here, one mirror here. They used to focus the two beams on the CCD camera or the material. The spatial filters, these two spatial filters of different magnification are used to increase the diameter of the laser. And finally, the object beam and the reference beam. Reference beam, as you can see, it is only a plane wave, and the object beam, which contains the information about the object, is allowed to overlap on the CCD camera or on the material. If it is allowed to overlap on the CCD camera, it is called a digital holographic technique. So coming to the applications of holography, the main application is in security, that which is very familiar to everybody and well known. Then biomedical applications are there, holographic interferometry is there, holographic optical elements, then holographic display, and finally holographic data storage. So security holograms, now everywhere holograms are used for security. Why they are used means security holograms are very difficult to forge. They are replicated from a master hologram which requires expensive, sophisticated and technology advanced equipment. It is found in credit cards, passports, ID cards, books, DVDs, etc. Used widely in many currencies. So these are the stickers which is manufactured at CDIT, Center for Development of Imaging Technology, Government of Kerala, where I was carried out my research. So they are the commercial producers of hologram stickers for Kerala State Beverages Corporation. So these are some of the images, hologram sticker, hologram tape, and some of the images that they are used for labeling used for making labels for the Kerala State Beverages Corporation. So the starting, the MasterCard used security holograms in the year 1983, and they became the first to use hologram technology in bank card security. And after that, in 1984, National Geographic magazine was the first major publication to put a hologram on its cover. This was the starting, but nowadays it expanded very much, and everywhere for books, for credit cards, for all the things, people are using holograms for security. And as an advance, one of my student is doing research in e-certificates by embedding computer generated holograms. So nowadays everything is online. So e-certificates are coming into the market. Now some of the universities are using e-certificates also. So for providing security to these e-certificates, we can embed computer generated holograms containing the biometric data of the student, and it is a very good the very good idea, so that we can keep the secrecy, or we can find out the authenticity, ensure the authenticity of the certificate provided by a university. So the biomedical application, it is mainly in medical education. So it is widely used in US and Europe. It's mainly used in medical education. As you can see, a 3D model of the internal organs can be made, and it is very easy for the medical students to study the features. That means they will get a three-dimensional view, so that it is very easy to understand the functioning of the particular organ. And also another one, apart from medical education, biomedical application microscopy will get a magnified view. So increasing the magnification by viewing the hologram with a longer wavelength light beam. So it's used for 3D images of microscopic objects, especially DNA and viruses. And another use is in holographic interferometry, which is called a non-destructive testing. Non-destructive testing. That means you can find out the faults in the substances, or on the some of the materials without destructing it. So you can use the holographic technique to find out the cracks, or the cracks or aberrations, etc., the deformations in the materials using this particular holographic technique. So it is used widely in numerous laboratories for non-destructive testing, and it visually reveals structural faults without damaging the specimen. And another area is holographic optical elements. That is lenses, filters, beam splitters, diffraction gratings. All these are available. So these are the optical devices. So all these devices can be manufactured or recorded as holograms. That means holograms will perform the function of lens. Even if it is a lens, sorry, it's a hologram, it can be used as a lens, or it will give the function of a lens or a filter, beam splitter, etc. So holographic optical elements, these holograms are called holographic optical elements. That means they are holograms, but they will give you the functions of lens, filter, beam splitter, etc. So instead of using a physical lens or a filter, you can use a hologram instead of a lens, filter, etc. So holographic optical elements are optical elements such as a lens, filter, beam splitter, diffraction grating, etc., produced using holographic imaging techniques. The interference pattern records the information of the object. When the object is a lens, the interference pattern reconstructs the optical element which has the function of lens. For this, what we are doing is we will place the object as a lens. While recording, the original object it will be a lens. Using the lens, making the lens of the object, we will record a hologram. And after that, we will remove the lens. So when you illuminate it with the reference beam, the hologram will act as the lens. So that is the property. This is our area of holographic data storage. This is a highly advanced area. Nothing is available in the market in the level. It is stored holographically, but it is an emerging area and it will come to the market within 3 to 4 years. It is under research. So as you can see, it's a size HVD. That is a device named by the technology holographic data storage. Holographic versatile disk. HVD. Holographic versatile disk. It is having the size same as that of a CD or a DVD, but it is having a huge capacity that we will see later. It's having high density storage. That is the peculiarity of holographic data storage. Then how this high density is occurring? That is the thing we have to study. So it's a high density, high transfer rate data storage device, HVD, holographic versatile disk. So holographic data storage, why we need a high density storage? As computer systems continue to become faster, they will need a way to access large amounts of data in shorter periods of time. And also, the magnetic and conventional optical data storage technologies are approaching physical limits beyond which individual bits may be too small or too difficult to store. And in holographic data storage, an approach of storing information throughout the volume of a medium, not just on its surface. So we can call it as a volume storage technology. In CD, DVD, etc., all these are surface storage technologies, but here the data or the information is stored in the volume of the material. So the holographic memory is a three-dimensional data storage system at high density inside the crystal. Crystal means it's a lithium, example, a lithium niobate crystal. It's a recording material or the photopolymer. Both these, as I have told earlier, is a dry processing materials. So with the rapid increasing demand for increased storage capacity in a small space, this technology offers an economy in price. So hence, holographic data storage has the potential to become the next generation storage over conventional storage system. So this is the comparison diagram showing the conventional optical disc and holographic optical disc. So in conventional optical disc, you can write a 0 and 1 in the surface of the material. That means the zeros and ones means you need a space to write a 0. A 0 means with pits and flats. So using laser, you have to burn or not burn the surface of the recording device. So zeros and ones, pits and flats, burn the space or not burn the space. So combination of 0 and 7, that means you need a space to write either a 0 or a 1. So these are surface storage devices, which means you need a space to write the zeros and 1. You can make the space very small, micrometer or some nanometer, but beyond a limit you cannot reduce the area for writing either a 0 or 1. So these are surface storage technologies. So 1 bit data means either 0 or 1. So data are recorded onto the surface as bit by bit in CD or DVD system. But in case of holographic optical disk or holographic versatile disk, it is volume storage means this entire data, that is a page data is shown here, which contains some 60,000 bits. It is focused onto the same spot on the material. That means the area you have used here for recording or for writing a 0. Therefore, on the same spot, you can write one page. That means you can, using a lens, you can focus the entire page. This is a modulated page that I will tell you later. So this is the modulated page means the beam contains 60,000 bits of data, of zeros and ones. So this is called one page. It's a resolution. Usually we will call in terms of resolution. One page, for example, 1024 by 768 pixels, or some 2000 by 1248 pixels, etc. So when you multiply it, it will give some like this, some 60,000 bits. So one entire page consisting of these much pixels is focused onto using a lens. You can focus onto a small area on the material, And also one above the other you can store many data pages. They will not overlap. Only thing is you have to use a reference beam. Those are different reference beam. You can use the angle shifter reference beam or space shifter reference. So one above the other also you can store many data pages. So like that you can increase the density. So that's why it is called a page-wise data storage, and also using multiplexing techniques you can store many data together. So same area using a same spot which earlier you have used for storing 1, 0 and 1 is used for storing pages of data at a time. So if the density will be high. So this is in here page data are recorded into the volumetric recording layer. So it is called volume hologram. So the conventional optical data storage devices available in the market are CD, DVD, Blu-ray, etc. All these are two-dimensional or surface data storage technology, which means all these are written in terms of zeros and ones. So you need a space to either to burn or not burn the zeros and ones. But so it is limited. Storage capacity is limited, the density is limited, and the transfer rate is also low. The advantages of holographic data storage means it is page-wise storage, and it is three-dimensional data storage technology. It offers high density, offers fast data transfer rate. Faster data transfer rate means the reconstruction is also page-wise. That means when you are giving the particular reference beam, the reconstructed beam is also a page. It is not a bit. So in a single flash, we can say on a single memory address or a single flash, you will get an entire page. So we can call it as the data transfer rate is very fast, and is longer shelf life. The materials are having longer shelf life and highly reliable. So it is a technique for highly reliable storage. So these are the diagrams showing the comparison of the capacity of the existing optical data storage devices, and the capacity of the holographic data storage device which is coming into the market, HVD. So you can see the capacity of CD some 700 megabytes, capacity of DVD 4.7 GB, and the capacity of Blu-ray 30 to 50 GB. And what we are expecting in the market on the having the same size as that of a CD or a DVD, it can carry 1 to 4 terabytes of information. So the storage density expecting is 1 to 4 terabytes. So the first device coming into the market, holographic versatile disk, the manufacturers are planning to record around 40 cinemas. 40 cinemas. You can imagine each cinema will be some 2.5 hours or 3 hours duration. 40 cinemas can be recorded in a single holographic versatile disk. So page-wise data storage offers high density. So the density can be up to 4 terabytes. The features of holographic data storage are, it is the next generation data storage technology. One HVD, it is nearly equal to, which is coming into the market, it is nearly equal to 5800 CDs and is equal to 830 DVDs and 160 Blu-ray, on the capacity of 160 Blu-ray. The media ultra high density optical type, optical disc, and the encoding format usually used is MBUG to MBUG for H264 standard, and capacity theoretically up to 3.9 terabyte, and the usage can be used for data storage as well as high definition video and the possibility of ultra high definition video. It permits over 10 kilobits of data to be read and written in parallel with a single flash. So a typical value, the capacity can be increased or decreased according to the requirement. So all these are the basis of nowadays important of 3D holographic projection. So the components of a holographic data storage system is the blue-green argon ion laser, beam splitters to split the laser beam, mirrors to direct the laser beam, LCD panel, spatial light modulator. This is the device. This is the main device this is the important device used in holographic data storage, spatial light modulator. This is an electronic device actually connected to a computer. The common market it costs around some 10 lakh rupees. So spatial modulator, you having different panel size are available in the market. So this is the device which converts the modulates the light beam according to the electronic data pages given to it. So it's a two-input device. Spatial light modulator is a two-input device. It is having a LCD panel. This panel is very small in size. the panel is illuminated with the light laser beam, and also the panel is given the electronic data to be modulated. So according to the data available on the LCD panel, the light will either pass through or not pass through. So if the LCD panel is having dark portions, the light will not pass through. If it is having transparent portions, light will pass through. It's a on-off modulation. So after that, you will get a checkered pattern. So the special modulators are used to modulate the light beam with according to the electronic data or the page data we are giving. And finally, lenses to focus the laser beam, then the material, lithium niobate crystal or photopolymer, and finally, to study or grab the reconstructed pages, we need charge coupled device or the camera. So these are the components required for a holographic data storage system. The main component is spatial light modulator. So this is the schematic diagram of a holographic data storage system. As you can see, the laser is here. The laser beam, it passes through a shutter which is used for controlling the exposure time. It falls on the beam splitter. Here it is split into two. One is the reference beam and another one is the object beam. The reference beam, this is the one after reflection from the mirror, it goes directly to the photopolymer material. Now it is a continuously moving type photopolymer material arrangement. So the reference beam directly falls on the material, and you can see the object beam. After special filtering, there is a collimating lens which makes the light beam parallel. So after the collimating lens, it is placed some f focal length apart from the special filter. So the collimating lens makes the beam parallel. So this collimated beam illuminates the panel. So this is the panel of the LCD. Now I have shown the resolution as 1024 by 760. Different resolutions are available in the market. LCD panels with a different resolution. So LCD panel is the main component which we have to place it in the optical beam. So this is the LCD panel having resolution 1024 by 768 pixels. Here we have to give one more input, that is electronic data pages. There a pattern is shown here. This pattern is illuminated with light beam. On the output you will get the modulated beam. So object beam means it is the modulated beam. So that means the light modulated according to the data values in the SLM. And finally, it's an imaging lens. It is focusing so this is having an area. So using particular lens, you can focus it into a spot. So this entire page having 1024 by 768 pixels is actually this is a holographic image. It is focused onto a small spot. That means a single spot. This is called a Fourier hologram. Just onto the area and it is recorded. So you can see, now you can see the entire page is recorded in a single spot. And also one above the other you can write many pages because they will not overlap. Only thing is you have to retrieve back the pages with the corresponding reference beam. And if you want to reconstruct the recorded data pages, cut the object beam and illuminate the recorded hologram with the reference beam only. Then you will get the projected data page or the reconstructed data page, which can be grabbed using a CCD camera and can be connected to a computer. So multiplexing is a technique used in holographic data storage systems to acquire high density. So different multiplexing techniques are there. Some wavelength division multiplexing, shift multiplexing, angle multiplexing. Mainly used thing is angle multiplexing. That means the reference beam is rotated 1 degree, some 1.2 degree, 1.5 degree, etc., or 2 degree, etc. Each time, for each page, a corresponding reference beam is given. So it will be a key or a code for storing this particular data page. Only giving this 1 degree or 1.2 degree angle shifted reference beam, you will be able to retrieve that particular page. So it provides a secrecy also. There will not be any overlapping. One above the other, on the same spot, one above the other using angle multiplexing, you can store many data. So that is the peculiarity or that is the importance of the holographic data storage. So density can be increased by using different multiplexing techniques. So the spatial light modulator, this is the important device. It consists of 2D arrays of light modulating elements. Actually, the panel will be an LCD panel, liquid crystal display panel. so that it can respond according to the light falling on it. So we will call it SLM as a data mask. So object beam directly illuminates the panel of the SLM or the data mask. It is given to a lens and finally it gets recorded. So SLM consists of 2D arrays of light modulating elements. SLM converts the digital data ones or zeros into a 2D array of bright and dark spots, and it is used to imprint the data on the object beam. So these are some of the panels which we are using in our laboratory. So this panel is having a resolution 1024 into 768, and this is the panel of actually a mobile. In earlier days we used to use this also because the commercial SLM, as I already said, it costs around some 10 lakhs rupees. So we will not, the researchers or for experimental purpose we will not be able to buy such a high cost equipment, so we are forced to develop cost effective SLMs. This is one type by reverse engineering a mobile phone. It's a Nokia 3310 mobile. In earlier days we used to use this. It's having a low resolution, some 84 by 48 pixels. The requirement of the SLM is the LCD panel should be size of the LCD panel should be very low, because we are using the laser beam. We can only use a coherent beam. For recording a hologram, we can only use a coherent beam. That means a laser. So laser is the only choice for recording a hologram. So we cannot increase the dia above a limit. So there's a certain limits using a special filter. We can increase the diameter of the laser beam. So the requirement is the panel dia or the panel size should be as small as possible, so that the entire area can be illuminated with the laser beam. So this is one panel having resolution 84 by 48, and this is one panel having resolution 1024 by 768. So actually this is the panel of a projector, LCD projector. So this is the modulated laser beam. So what the data shown here in the particular LCD panel is modulated according to, this is what I have said. This is the modulated laser beam. So this is the cost-effective SLM which we made earlier in our laboratory. So this is an arrangement which shows, as you can see here, this is the SLM. It's a special light modulator or the LCD panel of a projector. Here the projector is here and it is mounted in the laser beam, and this is the holographic recording setup. So this is the vibration isolation table. The main requirement for producing hologram is it should be vibration free. So we are using a vibration isolation table with heavy damping mechanisms, etc., so that the recording will not be affected by the vibrations. And usually the laboratories are set up in underground because we can eliminate the noises coming from the moving of the vehicles, moving of people, etc. So anyway, for giving good isolation to the vibrations, we need a vibration isolation table. And on the vibration isolation table, we are placing all the optical equipments. And this here you can see the SLM. It's actually an LCD panel reverse engineered from a LCD projector. It's having a resolution 1024 by 768 pixels. It's enough for all our experimental purposes in the laboratory. And the commercial one available in the market is the famous one. So many types are available, but what we are used is LC 2012. It's manufactured by HoloEye. It's a transmissive liquid crystal spatial light modulator having the resolution as that of a computer screen, 1024 by 768 pixels. The wavelength range is from 420 to 800 nanometer, and the pixel pitch it comes from and the range 36 micrometer. So for recording data pages, the data stream is sent to the SLM as zeros and ones. So first the image you have to convert it into digital. That is the job of the spatial light modulator. If the input you want to record is an image, it's an analog image. First you have to digitize it into combinations of zeros and ones. So these zeros and ones are given to the panel. So data stream is sent to the SLM is as zeros and ones. Forms a checker pattern. One transmits lights and zero block light. The beam is split, that is a laser beam. One light passing through the SLM, that is called the object beam. The reflected beam, that is the reference beam. So here also the light from a same laser beam is split into two. One is the object beam and another one is the reference beam. For a conventional hologram, the object beam was the diffracted light from the object. The object was there and the light diffracted from the object was taken as the object beam. Here, the modulated light, that is the light passing through the panel of the special light modulator, or the output of the panel of the special light modulator is the object beam, that is the modulated light beam. So when the light beam passes through the LCD panel, it gets modulated according to the checker pattern available or the combinations of zeros and ones available in the LCD panel. So if there is a black one transmit light, zero block light. So like that, at the output you will get a digitized image. So the reflected beam is a reference beam. It doesn't contain any information. It is only a plain beam. So these two beams interfere in the medium to produce a hologram. So this is a diagram which shows the recording. So this is the laser. It's a beam splitter. It splits into two. This is the reference beam. Without any change, it directly goes to the recording medium. So this is the recording medium. So after splitting the reference beam like this, it directly goes to the recording medium. But the function of the spatial light modulator is, here you can see, this is the image which we want to record. So initially it is converted to combinations of zeros and ones. That means it is digitized. So it's formed as data pages. And these data pages, you can see the data pages here. The combinations of zeros and ones are grouped. The page, they are packed page wise. So the corresponding page of the corresponding images are given one by one to the spatial light modulator, the panel of the spatial modulator. And after the spatial light modulator, so a spatial light modulator is a two input device. The panel is illuminated with the expanded laser beam, and also an electronic data page is also given to the panel. So two inputs are available in the panel. One is the electronic data page, combination of zeros and ones, but having a high resolution, some 1024 by 768 pixels, and the panel is illuminated with the light beam. So the output, you will get a modulated laser beam according to the digital data pages you have given in the panel. So these digital data pages are focused onto the same spot or the same area. Usually it is in a bit area or a spot. We can record it in a spot using a lens. So the entire data page is recorded in the recording material. So this is the recording process. So here in the bottom diagram also, here also you can see, this is the page composer or the spatial light modulator having combinations of zeros and ones. The modulated light is coming here. A lens L1 is placed at a distance, a focal length apart from the spatial light modulator. And this is the photorefractive crystal, middle one, blue one, and it gets recorded within the volume of the material. So you can use the entire space, each and every point of the material to store the data pages, inside, outside, on the surface, on the bottom, everywhere, left side, right side, everywhere. If a single point is there, you can use it for recording the data page, and also one above the other. The same point can be repeatedly used for recording multiple data pages using different multiplexing techniques. So the density will be very, very high. So here the photorefractive crystal is a volume material. It records the data pages inside the material. So for retrieving the data, we have to give the reference beam. The addressing beam is shown here. When the addressing beam is given, the data pages are illuminated, and again you can place a lens to collimate it, and finally you can read out. This is the reconstructed data page. So read out electronics, CCD camera or CMOS array you can place here. Usually a CCD camera is placed at a focal length from the second lens. So the reconstructed data page is grabbed using a CCD camera and processed in a computer. So for reading data pages or reconstructing data pages, the beam is no longer split. That means only thing you have to address the data page. That means only thing you have to illuminate it with the reference beam. So reference beam is diffracted off the recorded grating hologram, so which reconstruct the matrix pattern or the checkerboard pattern. It is projected using an optic onto CCD, and it converts it into a data stream. So this is the reading data page. Here the object beam is no longer present. So after recording, we have to reconstruct it So you have to eliminate the object beam. You eliminate the path or just cut the path of the object beam, and the same spot which we used for recording the data page is illuminated with the corresponding reference beam. That means the same reference beam which we are used for recording it. Otherwise, we will not be able to reconstruct the data page. So the same reference beam is used to illuminate the recorded page, and we can retrieve. On the other side, you can see. So it is illuminated with the data beam, sorry, reference beam. The data pages are again generated. It's a detector, it's a photo detector. So the data pages are generated. Then finally you have to combine it. So initially it was converted to zeros and ones, combination zeros and. So finally you have to group it together so that it's a parallel to serial conversion, so that you will get the recovered data. So electronic data is from the modulator, sorry, from the recorded place. The images of the data pages are generated using a detector, and these data pages are used to form the recovered data. So the same thing, same diagram is repeatedly shown here. This is addressing beam. This part is recording or writing. This part is reading. So for reading the data pages, you have to address. This is address beam illuminated with the same reference beam, and finally you will get the data pages. These are some of the experimental setups. One experimental arrangement in our laboratory. So this is the helium neon laser. It's a less expensive laser which we are used in the laboratory. So you can see the object beam and the reference beam, etc. Here a small LCD panel is placed. This is the place of the LCD panel. This is the violet line. This is the line of the object beam. The red line shows the reference beam. So both these are allowed to fall on the same area of the recording medium. So we can record different data pages on the same area using this particular experimental setup. And the materials used is also very important. So nowadays the materials are under investigation. So many researchers are working to develop more and more dry processing material, but because in holographic data storage we can use only dry material. For experimental purpose we can use wet processing, but for a commercial product, for a HVD, sorry, HVD holograph acetate disc, we need a dry material. So the important dry materials are photopolymer and lithium niobate crystal. So the chemical formula is LaNbO3. It has high photodiffractive sensitivity and stability. It has a trigonal structure, molecular weight 147.9. It has a band gap energy 4 electron volt. All the major researches are carried out with lithium niobate crystal or photorefractive crystal. This comes under the category photorefractive crystals, which doesn't need any wet processing. Photorefractive crystals. So under the category of photorefractive crystals, lithium niobate crystal is the first one. And finally, the CCD camera, as you can see, all you are familiar. It's a charge coupled device. It's a very light sensitive device. It converts pixels in images into electric charge. It contains a separate value for each detector. So CCD is the mainly used photo detector to convert the or to grab the digital or the demodulated data pages. And already I said some of the multiplexing techniques for generating high density. You have to multiplex. So multiplexing means one above the other you have to store many data pages. You can use either a shift multiplexing. Shift multiplexing is space multiplexing. Here are some distance apart shift multiplexing technique. Angle multiplexing. Angle multiplexing means the angle of the reference beam. So 360-degree you can vary the angle of the reference beam. So many combinations you can try. A combination of shift multiplexing plus angle multiplexing. A combination of angle plus wavelength division multiplexing. Wavelength division multiplexing means different colors of lasers. As I already said, so many colors of lasers are available. Blue, green. A combination of blue, green is also used. Red, etc. So different wavelengths. So one entire layer is written using red laser. Above that, another entire layer can be recorded using green laser. Again, above that you can use a blue laser and you can write an entire surface. So these will not overlap because you have to retrieve the data pages with that particular wavelength only. And again you can use a red blue green, again combination red blue green. So using different types of wavelengths you can stack or store one above the other different data pages, and also a combination of these multiplications also you can use. So the holographic data storage offers high density. And what the main problem here, or why this holographic versatile disk is not yet come to the market, means the retrieving process is retrieving means the driver. So we have to buy a driver. It's HVD driver. The driver is it will not revolve with the speed of light. All this mechanical with utmost perfection also the mechanical drives will not respond with the speed of light. That means if in a HVD 40 cinemas are there, with the first one if you want to go to the last one, the mechanical drive has to turn with that much speed. So since the density is very high, it will not turn that much. So that's a difficulty. Anyway, it will get overcome and the product will come into the market in the near future. We can expect so. So using this multiplexing techniques or combination of multiplexing techniques, you can add, so store one above the other many data pages so that the density can be increased very, very high. So this is one of the device. This is a atomic holographic disk which is having is only an image available in the Google. It's a holographic versatile disk called as atomic holographic disk having a capacity of 10 terabytes, 3.5-inch atomic holographic drive you can see here. So the manufacturers claims that it can contain the informations in 20,000 DVDs, the write only read many, or 4,000 Blu-ray write only read many disk in one 10 terabyte 3.5-inch removable disk. So this is somewhat the picture of a holographic driver. Holographic drive. You can see this is the atomic holographic drive. They expect a capacity of 10 terabytes. And who are involved in this particular research is In-Phase Technologies, a venture of Lucent Technology. In-Phase Technologies, they are the main researchers in this particular area. The exclusive purpose is to develop high performance holographic data storage media and also high storage holographic devices also. So the media also under heavy research. So developing a holographic medium which is reliable, having a long shelf life, having an enough capacity, resolution, etc. So this is also very, very important. So in-phase technologies, which is a venture of Lucent Technologies, they are the pioneers in this particular holographic research area, and they are aiming to develop high performance holographic data storage media or materials. And the US government and other participants are donating $32 million for research. Large majority of research are focused at Stanford and IBM's Almaden Research Facility. And the impact. What's the impact of this particular technology in the impact in the society? The everyday user, he might not be notice the impact other than the more space for storage in his or her computer. But big beneficiaries are big business and internet. So they are the recipients or they are the well-wishers of this particular technology because they need high density storage and also parallel data readout or faster data readout. Both are equally important. High density storage also and also faster readout, faster transfer rate. If you can store so many data pages together, high density it's okay, but you have to retrieve it also in a very easy manner in a high transfer rate. So that's also very, very important. So both these are supported in this particular technology because I already said page wise, not bit wise, page wise reconstruction is happening here. So in a single flash of laser beam you will get an entire page having the size example 1024 by 768 pixels. So a single flash of light retrieves one entire page or this much amount of data, means the data transfer rate is very, very high. So the big beneficiaries or big business and internet, they require parallel data storage and retrieval which allows much faster computation times, a much faster data access for internet servers as well as much larger storage densities, and also it should be cost effective, cheaper cost for megabyte once in mainstream. We can expect the cost we can expect once it is in mainstream, the cost will reduce. Initially, the cost will be high. It's not available, but we can expect that if anything is coming into the market for the first time, the cost will be high. And in a due course, when the time passes, the cost will reduce and the capacity will increase. So like that also the cheaper cost we can expect per megabyte once in mainstream. The data can be used for data storage for libraries. Library data can be used, documents you can safely store and use. So holograms, as already said, they are used for security purpose, widely used for security purpose. You cannot tamper it. Once it is produced, it is produced. So data storage, the data books in the library or the important documents, they can be stored yeah, authentically or securely in this using this holographic data storage technology. So data storage for libraries, documents and so forth will be cheaper and take up less space and access will be much faster. So the interesting facts, these are not existing, these are only, we can read it in articles. So interesting facts is, with the predicted technology, a 1 centimeter cube laser tube, imagine a sugar cube size crystal, 1 centimeter cube of a crystal. In that, the researchers claim that we can store the information containing in this much number of 1.44 MB floppy disk and 14,000 or 14,286 700 MB CD-ROM. So that means the information that you can store in 700 megabyte CD-ROMs. What number? 14,286 CD-ROMs can be encoded in this particular sugar cube size crystal. And also the information, 40 information that you can record in 40 hard drives or 25 million books of Library of Congress. It's unimaginable, 25 million books of Library of Congress that you can record in this particular one sugar cube size crystal. So which reveals the high density, this is the focus on high density storage. So the density you can increase, but the material requirement, the surface or the volume requirement is very, very less. So these are the interesting facts, not the actual facts. So the researchers are claiming that in a sugar cube size crystal, you can record this much data, what you can store in hard drive, CD-ROMs, etc. And finally, it says that 25 million books of Library of Congress can be recorded in this particular 1 centimeter cube sugar cube size crystal. And also, it has been estimated that books in the Library of Congress, the largest library in the world, could be stored in 6 HVDs. So, 6 HVDs, holographic versatile disk. The entire information can be recorded in 6 HVDs. So, the density is high, readout is high, and also it is also secure data storage. It cannot be destroyed anyway. Once it is recorded, it is recorded. Only thing is you have to retrieve the correct data pages. So the secure data storage, we can call it as secure data storage. So it has been estimated that books in the US Library of Congress, the largest library in the world, could be stored in 6 holographic versatile disks. And also the pictures of every landmass on Earth, like the one shown in Google Earth, can be stored in 2 HVDs. And with MP4 ASP encoding, HVD can hold anywhere in between 4,600 to 11,900 hours of video, which is enough for non-stop playing for a year. So this is unimaginable, cannot imagine, but this is the reality coming in future. So this much hours of video can be stored in a particular HVD. So finally, on concluding, this is a technology that's around for 40 plus years. HVDs may be, holographic versatile disks may be the future of data storage technology. They are having huge capacity, they are having very fast data rate, and also they are smaller in size. So these three are the important parameters. Huge capacity, the storage density is very high, the data readout, that is very fast, what do you call, very fast retrieval, or the transfer rate is very far, and the material requirement, it is very smaller. We need a very less space for writing this high density data pages or high density of the data. And also it is parallel processing. Parallel processing in the sense, the in a single flash, so many bits or so many data pages you can handle. So likewise we can call it as parallel processing. So it meets the demand for a capacity hungry society. So nowadays, in every day, the storage capacity, the demand for storage capacity is increasing. So day by day, due to this internet technology, etc., the capacity or the density requirement is very, very high. So finally, this device, HVD, can meet some of the demands of the society by providing high density storage and also faster readout rate, and also the large market and little new competition, because it doesn't exist today, it will come in the market. So with these words I conclude my presentation. So I think you got an idea about this new and highly interesting technology, holographic data storage technology. Anyway, so some of you may be working in this particular area, some of you may be hearing it for the first time. Anyway, all of you are familiar with the security holograms. That I am sure everybody is familiar with this particular security holograms. So I think you have enjoyed my session. You got some idea about holographic data storage. With these words, I am concluding my presentation. Thank you for listening to my presentation. Thank you all.
Now let's move on to the questionnaire session. If you have any doubts, you may ask now by just noting down in the chat box. I will ask them one by one to the speaker. Ma'am, there is one question asked by Mr. Mukesh Kumar. The question is,
Okay.
how is white light holography different than conventional holography?
uh, White light holography is same as conventional holography, but the difference is in conventional holography, if you are recording it using a red light, you are using a red laser beam. White light contains this laser beam also. So in conventional holography, what we are saying is you have to reconstruct the hologram using this particular red beam itself. And the white light means it contains all the wavelengths. So for reconstruction, you can use the white light also. So only thing is it will detect only the red light, and the red light will get reflected and we will be able to see the hologram.
Okay, ma'am. There is another question by the same participant. The question
Hmm.
is, what is the necessity of spatial filter in holography?
The special filter is needed for storing the data pages. So actually in conventional holography, an object is there, we are illuminating the object. The light diffracted from the object is recorded. So when the light diffracted from the object is recorded means the intensity is there, and when you compare it with the reference beam, you will get the phase also. So the reference beam is for generating the phase. So like that you will get the phase also. So there is a solid object and the diffracted beam from the object is written or recorded in the plate. But in holographic data storage, there must be a device for modulating or encoding the data pages, digital pages into the light beam. So we need a spatial light modulator. This is a device which modulates the light beam according to the digital data pages which we want to record. So that's why in conventional holography, we doesn't need a special light modulator, but in holographic data storage, instead of that object, the special light modulator comes there. It's the device which encodes the digital data pages into the object beam. So for generating the modulated object beam, we need a special light modulator.
There is another question. The question is, what is laser cube?
Laser cube means a material. We are calling it as as I said, the sugar cube size crystal, or the lithium niobate crystal, or the photopolymer material, which is having a size of a cube. We will call it as a laser cube. Nothing more than that.
One more question is there. The question is, may
Okay.
you please explain how multiplex theater work for 3D movies?
3D movies in the sense, I'm not. Getting the idea? For 3D recording in this particular data storage, for data pages, the multiplexing means anyway you have to get a high density. Even if it is a movie, first you have to take the frames. Your question is in 3D movie. Anyway, you have to take the frame by frame. So if you are taking one particular frame, it is recorded. One above the other, you can have to record. That means there must be some way so that you can retrieve these pages. So if first page is recorded and above that on the same stage you are using the second frame, there must be a difference. So you have to use a multiplex that is mainly in the reference beam. So the reference beam can be angle multiplex or shift multiplex, etc. So as already said, the reference beam is having some 1 degree angle. It can be used for the first frame. The reference beam having 1.2 degree and coming from 1.2 degree angle can be used for the second frame of the same movie. Is coming from the angle 1.5 degree can be used for storing the third frame of the same movie. So like that, we can use multiplexing techniques to store one above the other. Otherwise, you will not be able to retrieve these pages independently. It will get overlapped. That's why multiplexing is used for acquiring high density.
I hope your doubt is cleared, Mr. Mukesh Kumar. There is another question which is asked
Okay.
by Shovan Nandi. So the question is,
Mm.
can holograms made be using one laser for the reference beam and another laser for the object beam?
One for the
One laser for the reference beam and another laser for the
mm.
object beam.
Nowadays, one collinear technology is developed for making this holographic versatile disk. It is under research, and normally we are not using two laser beams. Anyway, they are coherent. It's okay. We can use. For this collinear technology, they are using two laser beams. One for this object beam, another for this reference beam. It is called collinear holography. I didn't mention collinear holography here. It's there. It can be used.
I hope your doubt is cleared, Mr. Shovan Nandi. There is another question asked by Dr. K. Amuda. The question is, ma'am, can you give example for transmission hologram and reflection hologram used in real-time application?
That means transmission hologram and real reflection
Reflection
hologram are two methods of recording only. Uh, in transmission hologram, the method is the object beam or reference beam are falling from the same side of the material, falling on the same side of the material. On the other thing, you can store it in the volume of the material by by allowing to overlap the two beams from the opposite sides. So even as from a conventional setup, you can record both transmission hologram and reflection hologram. Only the material requirement, it should be a volume material. So having high immersion thickness must be high. And the same material, you can record a transmission hologram as or otherwise you can use a reflection hologram. If material is volume material, both can be recorded, transmission hologram as well as reflection hologram. Otherwise, it is not. If you are using a surface material, only transmission hologram or a thin material, only you can record a transmission hologram. I think it is clear.
I hope your doubt is cleared, Dr. K. Amuda. There is one more question left, which is asked by SIT EEE PSS Lab. So the question, sorry ma'am, that was not a question. That was a
Mm.
thanking message.
Okay.
Okay. Uh, so any more questions? If you have any questions or doubts, you can just note down in the chat box. Uh, there is one more question, ma'am.
Mm.
It is asked by Mr. Vijay Kumar S. The question is,
Hmm.
what is the exact capacity of one HVD?
Now I cannot say the exact capacity because it is under research only. People are aiming in the range 1 to 4 terabyte. Hmm. Anyway, it will be greater than 1 terabyte. So the standard size we can say once it comes to the market. Hmm. So anyway, it will be in the range 1 to 4 terabyte. And also one thing I had to add the earlier question, can you give an example for the transmission hologram, reflection hologram in real time? What the holograms in what if you have seen in credit cards, books, etc. All these are reflection holograms because white lights are reflected from this particular hologram, and we are getting a impression or we are seeing that particular image. So all these are real time examples. So the Dow in the what the credit card or the holograms in the books, in the certificates, etc. All these are examples of reflection holograms. But transmission holograms uh, can be seen only in the laboratories because we have to illuminate it, and on the other side only you will get the image. So it is, you can see in the laboratory or what exists in the market. All these are examples of reflection holograms.
Um, I hope there is no more questions. So I think it is time to wind up the session. I take this opportunity to thank Dr. Sheeja MK. Thank you, ma'am, for an excellent presentation. Your years of research, your ability to present the subject in such an interesting manner is really appreciable. I would like to thank you on behalf of all the members present here. I hope you all enjoyed the presentation. Thank you so much for your interest and attention. The next section will be
Thank
at
you.
2:15, and I hope all of you will join back. And this brings us to an end of the second session. Thank you all.